Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Maths 3, Differentiation, Part 1, Product and Quotient Rules. So basically what we're talking about here, you've already learned how to do the derivative of individual terms both in algebra, which you learned in Pure Maths 1. Also, as we've been working through the Pure Maths 3 material, you've also learned how to do the derivative of individual transcendental functions, such as the logarithm, or specifically ln x, e to the x, as well as trigonometric functions, sine x, cosine x, tangent x. What we want to do now is look at what do you do or how do you take the derivative when you have a product, a multiplication of two terms that are quite different from each other, like maybe an algebraic term multiplied by a trigonometric term, or an algebra with an exponential, or a logarithmic term with a trigonometric term. So when we have the product of two terms, meaning both terms have the x variable in them, and the two terms are being multiplied together, or as we get to the quotient rule, the two terms are being divided, then there is a specific formula to help us with the derivative of those combinations. So first, let's look at the product rule. So the product rule is doing the derivative. So here we're using our notation with differential, our derivative in terms of x of a product. So u and v. U represents the first term, and it's going to have an x in it. And v represents the second term, and it's going to have an x in it, or your variable, whatever your variable happens to be. And these two terms are being multiplied together, hence the product rule. So the solution to that, or the answer to that, is u times dv over dx, or dv dx, plus v times du dx. And this is in your formula sheet. The formula sheet that Cambridge gives to you does have your product rule and your quotient rule in it. However, it is, because you're going to use these quite often, it is nice to try to learn them in a way that is helpful for you to be more efficient, so that you're not always referring to your formula sheet unless you absolutely have to. So here's a little way to help you remember this. 1d2 plus 2d1. 1d2 plus 2d1. What does this mean? 1 represents your first term, u. D is just a nice way, or a little bit of kind of a mnemonic way of remembering the derivative. So 1 times the derivative, d dx, of 2, 2 being the second term. So 1d2 plus 2, that's the second term, times the derivative of the first one. So here you can see 1, first term, d2, that's dv dx, plus 2, the second term, times d1, du over dx. Okay, now let's look at the quotient rule. The quotient rule is the derivative of two terms that are being divided, one term divided by the other term. Again, this can be any combination of algebra or transcendental functions that you have learned previously. So to do the product rule, we have v du dx minus u dv dx over v squared. Well, again, this formula is in your formula sheet, but to help you remember it as you go through it, we have low d high minus high d low over the square of what's below. Kind of rhymes. Low d high minus high d low over the square of what's below. So this means low being the lower term in the fraction, low, so that would be our v. D again is just our description of the derivative. High being the high term. So here we have v, our low, d high times the derivative of the upper term, the higher term, minus, so subtract the higher term times the derivative of the lower term, high d low, over the square. So over means this is your divide, the square of what's below, or in other words, v squared, divided by over, divided by the square of what's below, v squared. So hopefully these little mnemonic devices will help you get these formulas into your mindset so that when you get to the mechanics of doing it, that you can remember these little mnemonic devices to help you be more efficient. Now, we're going to take this and go to the question types. But remember, this is just the skill. This is just the mechanics of doing it. We also need to apply it. And you're going to see that the applications will go back to even Pure Maths 1 and of course Pure Maths 3, things you've already learned, and then apply it to a situation. Okay, so let me set up the first problem for us. Okay, let's look at our first question together. And what we have here, we have this graph. It says the diagram shows the graph of y equals e raised with the power of cosine x times sine cubed x from 0 to pi, and m in the diagram is the maximum point, and the shaded region R is bounded by the curve and the x-axis. So for this part I is the part that we want to focus on. It says find the x-coordinate of m, show all necessary working, and give your answer correct to 2 decimal places. So here we have this product, and we need to find the x-coordinate of m, which is said to be a maximum point. So if you remember from Pure Maths 1, the maximum point is also known as a stationary number. And to find min or maximum, you take the first derivative and you set it equal to 0, and then you can solve for those minimum and maximum points. So in order to do the derivative, notice that our equation here is a product of an exponential and a trigonometric function. In fact, our exponential has a trigonometric function in the exponent. So this is quite an interesting combination. Let's go back to the board and just follow our product rule that we just learned. Okay, now before we do that, notice here that our domain is 0 to pi. We are dealing with trigonometry, so make sure that you set your calculator to radians. So remember, anytime you're dealing with solving something with trigonometry, check the domain, make sure you set your calculator first, and get that little R up in the screen for radians. That way you don't solve this all and get the wrong answer because your calculator's set wrong. So that's the first thing. Make sure your calculator's set in the right mode. Here we have maximum, so that means we need to do the derivative and set it equal to 0 for stationary points. And derivative now is what we want to apply, and we have the product rule, this exponential term that has an x in the power, and we have a trigonometric term with x in the argument, and we're going to do the product rule. So the product rule is, so our dy dx is going to equal 1, that is term 1, e to the cosine x, times d2, 1 d2. So the derivative of this second term. Now, this has an exponent. Remember what we learned just in the last unit in deriving trigonometry, that you do the exponent first, then the trig function, then the argument. So the exponent multiplies to the front, subtract 1. So that gives you sine squared x. Then you do the trigonometric function, the derivative of sine x is cosine x. Then you do the derivative of the argument, and I'll just put here a 1. The derivative of x is just 1. And so that's our 1 d2 plus 2 d1. Now we have to do the derivative of this e to the x. If you remember, the derivative of e to the x is e to the x, or x here is cosine x. Then the dx, the derivative of that exponent is a negative sine x. Okay, so here we have 1 d2 plus 2 d1. And our 1 d2 was the derivative of this trig function with exponent first. So that gives the 3 here and the 2 there. The trig function stayed the same. Then you do the derivative of the trig function. Then you do the derivative of the argument. And here are 2 d1, where our 1 was the exponential. And then we had to do the derivative of the exponent part, which is this. So kind of a lot of pieces. Now let's try to smooth this out a little bit. So here we would get a 3e cosine x sine squared x and cosine x plus, or actually minus, because we have this negative back here, minus e to the cosine x, and that gives us a sine to the 4th power x, and all of this has to equal 0 because of m being the maximum. Okay, so we worked carefully through the product rule. Then we just kind of simplify and combine things here to get this, and it's set equal to 0 for because it's a stationary point. Now is the solving part, and whenever you have a long statement like this equal to 0, you want to look at factoring possibilities here. So we have an e to the cosine x common to both terms. We also have a sine squared common to both terms. So we can take the e cosine x and the sine squared x, factor it out. That leaves us with a 3 cosine x minus, and if we take out sine squared, there's still a sine squared x there. Now, if we want to look at these first parts here, we know that e to the cosine x cannot equal 0. Remember, you cannot take a positive base, e is 2.72. You can't take a positive base, raise it to any power, doesn't matter what it is, and get 0 or negative. Okay, so exponentials always have to be positive, so it cannot equal 0, so that we don't have to worry about that term. Our sine squared x equals 0. If you square root, sine x equals 0, and if you inverse sine, you still get 0. However, the 0, if you go back to the graph, maybe I'll just show you really quickly here. If you go back to the picture, the 0, which would be right here, that would be a minimum. So it is a stationary value, but it's not the one we want. We want the maximum, and what we just found was the minimum. So we don't want that one. Okay, so this We'll just call it min. We'll not say that it can't equal it. It's just not the one we want. That's our minimum. So this is the one here that we're working with. Notice we have cosine and sine. Generally, if it was just cosine and sine, you could put one on one side, one on the other, divide and make it tangent. But this is a sine squared. So we can use our identity that we learned in Pure Maths 1 and also continuing into Pure Maths 3. This is 1 minus cosine squared x. Okay, and don't forget to distribute this negative here. So what we end up with is 3 cosine x minus 1 plus cosine squared x equals 0. And we notice now that we have a quadratic. So we get cosine squared x plus 3 cosine x minus 1 equals 0. And you should recognize that this does not factor. The factors of 1 cannot subtract to give us 3. So we're going to have to use the quadratic formula. So if we just bring this right up here, and this is our value that we're solving for in a quadratic formula. If you remember your quadratic formula, ax squared plus bx plus c equals 0. This is the b on the x, ax squared plus bx. So in your quadratic formula, when you get x equals the negative b, that whole formula, this is the key right here that you're actually solving for. So our cosine x equals a negative b, negative 3 plus or minus root b squared, so it would be 9 minus 4 times a times c. Hopefully you can see that there. 1 times a negative 1 squished there into the end. And all over 2a, 2 times 1. So this is a negative 3 plus or minus root 13 all over 2. And when we do that on our calculator, we get cosine x equals a 0.302775 is one of them. The other one that we get, I'll just put it over here. When we do the minus part, we get a negative 3.3027. Now, right away, hopefully, you'll remember from trigonometry that sine and cosine fluctuate, that is, or oscillate, go back and forth between 1 and negative 1. This goes to negative 3. So this one we get to throw out. We can throw it out. It cannot equal this. Besides, if you tried it in your calculator, it wouldn't work anyway. Remember, we're in radians, and you would get an error. You get an error message. So cosine and sine and cosine cannot be greater than 1 or less than negative 1. So you can try it on your calculator if you want to, but you're going to get error message. If you recognize it right away, you can just throw it out and save your time. And so this is the one that we want over here. So we want to take the inverse cosine. So x equals the inverse cosine of this value, 0.302775. I just took a lot of decimal places there. And what we get is x equals 1.26. That is our answer. That is the x coordinate. I guess you need to see it there. X equals 1.26. That is the x coordinate of m, which is the maximum, and it is between 0 and pi. Remember, pi is 3.14. So 1.26 is between 0 and 3.14. So it fits the domain, and it is the maximum value of the graph that we saw. So that's our first question. Notice the product rule is what got us into the application of the question. So the mechanics of doing that's very important. because your result then moves forward into the application, and you want to, of course, make sure that you get start with the right, the right values there. And so let me set up for the next one. Okay, let's look at our second question here. This time we have a quotient. It says find the exact coordinates. So exact meaning we can't use decimals. Coordinates means it wants both the x and y coordinate of the point on the curve y equals x divided by 1 plus ln x, at which the gradient of the tangent is equal to 1/4. So exact coordinates, no decimal, find both x and y, point on a curve. Our curve is a fraction or a quotient with an algebraic term on the top and a logarithmic term on the bottom. And gradient is slope, which also should connect your mind to derivative of the tangent is equal to 1/4. Okay, so here we have our equation on the board. The gradient is 1/4, and this is, remember, the application or the general algebraic application of derivative is slope. So that tells us that we need to do the derivative. So if we do the derivative here, we get dy dx equals. Now we need to remember our quotient rule. So low, so that's all of the low, what's below the division bar. D high, and the derivative of x is just 1, minus high d low, well, the derivative of 1 is 0, and the derivative of ln x, remember, is 1/x. So you might need to look at your formula sheet. You also might need to go back to the video where we covered that with logarithms. And so the derivative of ln x is 1/x. So we get a negative 1/x here. And we have now 1, so low d high minus high d low over the square of what's below. And this is equal to 1/4. Our slope is equal to 1/4. Now, what we want to do is clean this up here a little bit. And okay, we want to clean this up. I just noticed and I checked that I had made a mistake in writing the problem. This is actually 1 plus, if you go back and look at where I showed you the question, this is actually 1 plus ln/x, meaning that this here is just a positive 1/x in here. Okay, so I had written that incorrectly. So now we want to clean this up, and what we get is a 1 times this is 1 minus ln x, and then these cancel and we get minus 1. Okay, equals or over our 1 minus ln x squared. And now what we want to do is we want to multiply that out, and we're going to get so that because this was 1 plus ln x, this is 1 plus ln x, I have to change this to plus here, and that. So kind of had to follow through with, because I wrote it wrong. Always make sure that you carefully copy your questions. Students, I noticed, do that a lot. They copy a question wrong and then get the problem wrong. And I noticed that I had copied it wrong and it was following through in my work. So this is plus, makes this derivative of that plus. This here, again, should be plus, and this one here should be plus. So I think we've got all the, it's amazing how one little sign carries through all your work, messes everything up, but I think we're on track now. So low d high minus high d low over the square of what's below. And now we can simplify here. So this on top just becomes ln x. And on the bottom, if we multiply this out, expand it, we get a 1 plus 2 ln x plus ln x squared. Okay, so if you need to, you can write this out 1 plus ln x times 1 plus ln x. Do not distribute exponents over add or subtract. It means you have two factors of it, and so you need to do basically your smiley face method here. This times this times this, there's your nose, there's your mouth, and you get this here equals 1/4. So when we work this out, we get 4, cross multiply, 4 ln x equals our ln x squared plus 2 ln x plus 1. Subtract this to the other side, our ln x squared. So if we subtract 4, we get a minus 2 ln x plus 1 equals 0. And now this is a quadratic. It does factor. The factors of 1 that add up to 2 are 1 and 1. So the factors of 1 that add up to 2 are 1 and 1. So we get a ln x minus 1 squared equals 0. So negative 1 times negative 1 is positive 1. A negative ln x and a negative ln x makes a negative 2 ln x. And ln x times ln x is ln x squared. So this factors. You could use the quadratic formula, you'll get the same thing. And so if you square root 0, you just get 0. Let's bring this up to here. And we now get ln x minus 1 equals 0. When you square root both sides, still 0. Cancels your square. Bring the 1 over. So we get ln x equals 1. You can do this on your calculator, but hopefully you remember that the base in your logarithm here, this ln is base e. And so basically e to the power equals the argument. So x equals e to the 1, which is the same thing as just e. So that's our value of x. Now we want to take that, because it says find the coordinates, plural, both the x and y value. We want to plug this into our equation here to get the y part. So we're going to get an e over 1 plus ln e. And when you have a ln e, that's just 1. You can put it in your calculator. It's basically saying e to what power is e? Well, e to the 1 is e. So this is 1. And so what you're going to end up with is e over 1 plus 1, which is e over 2, or half e. So our point, the point P that we're looking for, has the coordinates of e and 1/2 e, or e over 2. This is our solution to the second one. So we had our curve, we have our our quotient rule being applied with the slope. And again, slope implied the derivative in the first place is equal to 1/4. Then it's just a matter of algebraically working through all of that, recognizing your quadratics, even though it's with logarithms. Just remember, all of your algebra still works the same outside of the transcendental functions, whether it's e to the x, ln x, sine x, doesn't matter. Your algebra on the outside all works normally. And then you have some of your transcendental function aspects that you have to work with as well. And we have our answer here. Okay, I have one more practice problem for us. Okay, let's look at our last problem. and says the curve, again, you can see the code up here. It's from Winter 19, paper 32, number 2, if you're interested in that. The curve with equation y equals e to the negative 2x divided by 1 minus x squared has a stationary point in the interval from negative 1 to 1. Find dy dx and hence find the x coordinate of this stationary point, giving the answer correct to 3 decimal places. Okay, so they didn't show us the graph this time, but they did say that there's a stationary point that exists somewhere between 1 and negative 1. That's what we want to find. And of course, stationary point means that we need to find the derivative and set the derivative equal to 0. And so when we look at this, we see that we have this quotient. We have an exponential on the top and an algebraic term in the denominator. So we're going to do our quotient rule. Dy dx equals low d high. So the d high is an e to the negative 2x. So remember, e to the x is e to the x. Then you have to do the dx, or the derivative of the exponent. So that's a negative 2 is the derivative of the negative 2x. So low d high minus high times d low, which the derivative of 1 is 0, and the derivative of a negative x squared is a negative 2x, all over the square of what's below. Okay. Now, if we want to kind of simplify this a little bit, here we have a negative 2 times this. So let's put our e to the negative 2x here, times negative 2 times the 1. So that's a negative 2 plus 2x squared. Guess we'll do it that way. Just distribute the negative 2 in here. Negative 2 plus 2x squared. We'll leave the e to the negative 2x out here. And this then becomes a plus 2x e to the negative 2x, all over our 1 minus x squared, the square of what's below. And because we're doing stationary point, this has to equal 0. So because this equals 0, it basically cancels out our denominator. If you just multiply the denominator to the other side, it disappears into the 0. So what we're left with is really the top, and we can factor out that e to the negative 2x from both sides. And that's going to leave us this 2x squared plus 2x minus 2 equals 0. So just factor out that e to the negative 2x and get all this algebra, this quadratic 2x squared plus 2x minus 2. This one, this denominator here just multiplies into the 0 and cancels out. So again, remember, an exponential cannot equal 0. So we can get rid of that one. We don't have to worry about that anymore because this is product. So if it's product, then that means either this equals 0 or this one equals 0. So don't forget your 0 product rule. And this one cannot equal 0. What that means, this one does need to equal 0. We can also divide everything by 2, and the 2 will disappear into the 0. So we get x squared plus x minus 1 equals 0. When we divide everything by 2. Now as we look at this, you notice that this cannot factor. The factors of 1 cannot subtract to give us 1. Factors of 1 are 1 and 1. They don't subtract to give us 1. So this does not factor. You have to use the quadratic formula. So if we bring this, let's bring this up here. So x equals a negative b plus or minus root b squared minus 4ac all over 2a. So that gives us x equals a -1 plus or minus. Here's a positive 4. 1 plus 4, that's root 5 all over 2. And then when we solve this, we end up with x equals 0.618. And we also end up with x equals a -1.618. However, after you solve algebraically, algebra gives you the possible values for the construct that you're using. You need to go back and look at the context. And the context says that the stationary point is between 1 and -1. This one is outside of our parameters. So we're going to throw out that one. And so our answer is just the x equals 0.618. So after you solve, go back and just read the question again. And sometimes there's these things. Sometimes it says the answer is positive. In this case, it gave a domain. And just go back and that you might not recognize the purpose of it at the beginning of the question. So after you solve, go back and check to see if there's any kind of restrictions like that. And that way you identify the correct value. X equals 0.618. So there's our product and quotient rules for derivatives. And thank you again for joining me in the Zoom room. And I hope to see you again next time.